Yeah. Okay. Thanks, Chris. Yeah. So just I won't dwell too much on this. Chris has introduced us. So yeah, I work across most of our nuclear new build portfolio, whether that's energy or defence, very much on the civil structural side of things. And Steve actually lives and works out in India at the moment with our team out there, working as Chris just explained, just as he described. What we're going to do today is we're going to present to you a bit about Hinkley Point C. I'm sure some of you know all about it, and some of you probably know a little about it. So we'll just give you a brief overview of that, and particularly our involvement on Hinkley Point C around the structural design of what's called the conventional island balance of plant. Then spend a bit of time about digital engineering in structural reinforced concrete design. And then I'll hand over to Steve, and Steve will talk about the work we've been doing around 3D reinforcement detailing and the benefits that can bring to any project, let alone Hinkley. So a bit about Hinkley then. So you're probably all aware of it. First nuclear new build energy power station in the UK for about 40 years. Once it's up and running, which is targeted for 2026, 2027, it will produce 7% of our country's low carbon power need. So it's going to be a significant part of the energy mix once it's up and running. So that's energy for 6 million homes. And during construction, it's generated about 25,000 employment opportunities, huge investment in the Southwest. About 64% of the investment is going to UK companies. So this is, as you know, a major infrastructure project for this country, indeed for Europe. We got involved quite a long time ago now. In first the contract we got involved in was the design of the technical galleries. So there's not shown on that diagram, there's about 8 kilometers of cut and cover tunnels basically around the site. Tunnels makes it sound very simple. Some of them are nice, simple, just square rectangular cross sections. Some are basically underground buildings where all the galleries cross over and interact and interface. Then the classified buildings, so that's the buildings associated with the pumping of the cooling water around the site. So those are the buildings in green. They look fairly innocuous on that drawing, but they significant embedded depths with all the pumps and filtering systems and so forth, taking the water from the channel, cleaning it up and then putting it around the system. The unclassified buildings, they're unclassified by name. They're not, when we talk about classified and unclassified, we're talking about seismic and safety classification. The unclassified buildings is a bit of a misnomer because some of those buildings do have a seismic classification as well. But what you can see there, those big 2 big blue buildings in the middle, those are the turbine islands, the turbine halls, significant steel frame structures, and we were responsible for the concrete substructures below those. The ancillary buildings, those in green, smaller supportive buildings, and then for the buildings in blue, those were the ones we got involved in just in the 3D RC detailing a bit later on in the project, helping other parts of the project deliver the 3D RC detailing. A few facts and figures. These numbers are out of date now, but they give you just a sense of scale. Total reinforcement bar length, I think this was as detailed at the time, 27,000 kilometers. 91,500 tons of reinforcement, 12 million pieces of reinforcement. It actually says 10 kilometers of underground tunnels there, 33 buildings in total, and that's the number of drawings we've produced through this. And we'll come on to the 3D RC in a little bit. Obviously, faced with a program like this, a project like this, program pressures, the high degrees of repetition in terms of the design methods, the analysis methods, and the detailing. A huge opportunity for digital delivery, but big drivers for digital delivery as well. And this whole idea of left shifting, which again is a term we're talking about more and more in industry, bringing some of the thinking that would often happen later on in the process, in the project process, maybe during construction or pre-construction, bring it to the left, thinking about it early on, a bit like the previous presentation, that whole thinking about how it's going to be built. Not just making sure it's buildable, but designing it as it's actually going to be built. So yeah, significant opportunities for that. And then in terms of automation, which is what I'm going to talk about in a second, just a huge drive for how do you deliver such volumes of analysis and design in a cost-effective program effective manner. And so, yeah, we looked heavily into automating our processes. That's what I'm going to talk about now. So we developed a tool, a software called Contour RC. Now, the reason we did this was multiple. I've already obviously explained the benefits of automation in terms of productivity, in terms of program. On Hnckley, we're faced with a non-standard code of practice. It's called ETCC, and there's a UK companion document and a number of other project-specific guidance notes. These were developed through what's called the generic design assessment. So this is the approval process where the regulator approves the EPR, the concept, the nuclear plant and power station. And these were, in terms of conventional design, largely based on the Eurocodes, but not entirely. And then a large number of seismic requirements as well that were not in line with Eurocode 8, but were more in line with US codes of practice. So project-specific codes and design guidance that your normal software, your normal packages wouldn't cater for. Plus, we're looking at really quite high-end finite element analysis here. Huge volumes of load cases and combinations, large volumes of data, as you can imagine. Lots of permutations of thermal load cases and seismic load cases, which we analysed in Abacus, a general finite element analysis package, which meant, okay, again, you don't have the design modules to go hand in hand with that. But also, by developing this tool, it gave us complete autonomy and flexibility on how we developed it and how we accessed it and how we modified it. And that proved really helpful later on in the project process when changes come along or the client wants to understand a little bit more, interrogate a little bit more about what's going on somewhere specifically in the building. It gave us complete autonomy and flexibility to be able to recode it, represent data, reprocess data. So that was not necessarily a benefit we planned at the beginning, but certainly one that came out as we went along. And of course, another big advantage of automation is the quality side of things, the standardization, minimizing the risk of human error. Also high quality in terms of the deliverables, consistent automated reporting of the outputs, which then helps with the whole review process. It's a very onerous review process, as you would expect and want on the nuclear power station, with multiple tiers of review, but being able to standardize the outputs meant that the review process got slicker and slicker and slicker. I'll briefly touch on this, but then I'll move on to a video and I'll take you through the video of how Contour RC works. But if you go from left to right, step one is your finite element analysis. So the good thing about Contour RC is we can interface with any finite element analysis, whether that's Abacus or ANSYS or Robot or other tools. Taking that data, doing the concrete shell design. So it's a shell design sandwich model approach as per Eurocode 2 and XLL. Determining the theoretical reinforcement requirements, and that's the calculation part of Contour RC. Out of that, we can output all the acceptance criteria and so forth. What we then do is we then overlay, we then plot the practical reinforcement provisions. So you've got these theoretical contour maps. We then decide, and this is where the collaboration with the contractor comes in, actually practically how do we want to reinforce this? What you can then do is then you can then put that back through the process, and what you end up reporting is the actual utilization ratios, the actual performance against the acceptance criteria, the actual densities, and so on and so forth, against the reinforcement that's going to be detailed, not just the theoretical reinforcement that was needed. And then we output those and it goes through the reporting process and the review process. And it also provides us the high quality communicative deliverables into the 3D modeling stage of the project. So I'm going to try and play a video, and I'll stop it and start it because it does go through quite quick. Just take you through the steps. Okay, I'll just click on it and pauses. Yeah, okay. Okay, so that's the process as I just described it. As I said, we can we've developed this so that we can interface with any analytical tool, and it also means we can interface with any form of structural analysis, whether it's seismic or blast or thermal, the output, so the input into Contour RC is basically just your internal force resultants. Obviously, at every single node in the mesh, every single panel, every single case, and then all the combinations are built within Contour RC. So one of the inputs into Contour RC is your combinations table, if you like. On a project like Hinkley, where you've got seismic and thermal, as I was just describing, blast and hydrodynamic effects and so forth, you can end up with thousands of combinations. But this ability to interface with other software has yielded a number of benefits when we've used this on other projects as well. Wiggling building. Okay, so it's got a very accessible user interface. You input certain inputs, not just your folder structure and so forth, but your acceptance criteria. We've now developed this with modules, so we design for ETCC, but you can also design for Eurocode 2 or ACI or other project-specific codes. And we take all those design outputs, I can't go back, and overlay that, the mesh and the data into the 3D geometrical model, sorry, and then you can do your overlays and select your reinforcement. Need to pause this a bit quicker. There you go. So what's reported there is your contours with your reinforcement. You can decide beforehand what reinforcement provisions you want to consider. So depending on contractor preferences or what's available, you may just want to limit yourself to the same by diameter at consistent centers at 200 centers. You may be willing to consider, actually, I'm quite happy to mix my bar diameters. So what we do is we input only the reinforcement provisions we want to be considering on a particular project. You mark up your final designed reinforcement provision, assign it the properties, and then you've got your data that you can feed back through your calculation process to report the actual design utilizations. At this stage, we would then be talking to the contractor, saying, which was by law on Hinkley, and saying, right, this is what we intend to brief for the detailing stage. Is there anything we need to be adjusting here for your benefit on site to ease fabrication? And then, like I said earlier, we can automate all the extracted results. One of the things that was particularly of interest was how much margin do we have in the design for seismic. So we need to design for a 1 in 10,000 year earthquake, but we also need to understand on a nuclear project, how would it behave if it was a 1 in 10,001 earthquake or a 1 in 15,000 earthquake? And we don't calculate that specifically, we don't design for that, but we really need to be able to understand what the margin is in the design. So one of the functions we have in Contour RC is not only to be able to put the final reinforcement provision back through to check the actual utilizations, but also progressively increase the seismic demand to recalculate the margins. Now, you could do that more crudely, if you like, just by looking at utilizations, but this gives us a very precise assessment of the margin every single location around every single of the 33 buildings that we designed. And that's a key part of then the safety case that will then go through, obviously, the client review process and ultimately to the regulator. Okay. I think I will probably move straight on to Steve because time is pressing. And I think I've covered everything on there. Actually, that's an interesting one. So where it says there, granularity of results, ductile, brittle, failure, hierarchy, contour maps. What we're able to do is, because we report against all of the acceptance criteria we have, whether that's stress limits or strain limits or crack widths, and because we do that margin assessment against all of those acceptance criteria, what we can then report is actually for a given element, is the first failure going to be a ductile type failure, like tensile failure of the flexural reinforcement, or is it going to be a brittle type failure like compression of the concrete? And again, that's really important to understand because we want reliable inelastic or reliable ductile behavior beyond the design cases that we've designed for, because we need that robustness should something come along that's greater than what we've actually designed for. So again, that's really helpful in terms of the ability to interrogate the data and present it and substantiate it. Okay, Steve, should we move on to you?
Yeah, perfect. Thanks very much for that, Dave. If you just flick onto the next slide. So I'm going to tell you a little bit about 3D reinforcement modeling, what it is, what benefits it brings, and how we've applied it onto the Hinkley Point C project. It will be a little bit of a whistle stop. Normally, when I do this presentation, I only do it over an hour, so I've had to compress it down. So I do apologise that in advance. So firstly, answer the questions: what is 3D reinforcement modeling? And what it is we'll take the designs that have been produced from the structural designer, in this case from Contour RC, and we'll convert them into a 3D model that will have every single reinforcement bar modeled with its exact sizes, bends, in a model, so that we can really visualize how it all comes together. And we can start building these models and building into these models information from both the designer and from the contractor. So as Dave alluded to earlier, we don't want to just design and detail for how it could be built. We want to design and detail for how it is going to be built out on site. And we work quite heavily with the contractor in this to understand where their construction preferences are, how they're going to construct it in terms of sequencing, so we can get our detailing right. And by doing it in 3D, we can then start to visualize all this information and all this detail. We're also able to start declashing elements, because now we've modeled things in 3D. We can then run clash detection from both a reinforcement to reinforcement point of view, but also a reinforcement to embedment items. So being a nuclear power station, the regulator's requirement is that we're not allowed to post-drill and fix any embedded items. So that means that everything has to be cast in place to start with. This means that by doing it in 3D, we can now coordinate those elements, so we have greater degree of coordination and alignment between the civils works and the follow-on trades, such as mechanical and piping work. Dave, if you could just flick on to the next slide. So why do we do it in 3D? We've obviously, for a large number of years, produced standard 2D drawings, and things have managed to be built. So why move to 3D? It's really to do with the fact that we're taking on this left shift challenge. We're taking issues that would be dealt with out on site and bringing them into the design phase, and resolving them when we've got time to resolve things the right way, and also when the cost to resolve them is cheaper. And this will help to ultimately provide further confidence to the site-based activities and reduces the risk out on site. So as I've said, we've got, by modeling 3D, we can understand the sequencing. So we've got high confidence in terms of the buildability and the bringing in the way the contractor wants to do it. We can then fully coordinate against the temporary works as well. So the contractor can come in and model their reinforcement, their chairs, their lifting anchors, etc., around our reinforcement, so that they're not trying to just squeeze things in on site. And also by modeling 3D, it really helps to improve the safety of the work going out on site, because everything is modeled spatially correct. So we can start running sequences to make sure hand access isn't going to be a problem. We can tighten the couplers. And for Hnckley, we can start to embed a lot more prefabrication, which will help to reduce the need to work in confined spaces, for instance, during these cut and cover tunnels. And that's the sort of benefits to the contractor. But for a designer's point of view, we also gain a far higher degree of confidence that our design has been taken into the drawings, into the construction deliverables in an accurate manner. We're also able to produce further clarity on our drawings, because ultimately, more often than not, the drawings are still the contractual deliverable, and producing these from a 3D model, they are just views of the model. So we're able to add more sections, we're able to add more plans and elevations to show the information clearer, and we can add a lot more information to the drawing. So for instance, on Hinkley Point C, we provide the setting out of all of our reinforcement bars in both the X and Y direction, so that we've got that confidence that our when it gets checked out on site, they're able to interpret our drawings a lot clearer. And ultimately, all this means to the client is that they're going to have less site queries, they're going to have a more efficient construction, and ultimately it provides better cost and program certainty. Dave, if you just flick onto the next slide. So when we talk about 3D modeling, the modeling outputs are firstly, it's the physical model itself, and this is more than just a model. This is a place where we have a lot of data embedded into itself. So all of our reinforcement bars contain all the information necessary for fabrication. They also contain their location information. So we've got a special coding system, so we can find out where every single bar that's from the model, where it is to go out on site. And this also then feeds into the ordering system. So the contractor can order their reinforcement directly from the model. It goes straight to the fabricator with fabrication information. And we also know when it comes to site, we've got all the location information. So it means that the contractor on site has got less logistical challenges, and they've optimized all the handling of all the material around the site. We also, as I've alluded to earlier, the model would be declashed both bar to bar and bar to embedded item. And unfortunately, I think the video is already played. I don't know if you could play that video on the right-hand side again there, Dave. Yeah, so we're working with the contractor. We're also allowed to digitally rehearse all of our reinforcement being fixed. So this means that not only will it be in a declash position in its final but permanent position, but also while fixing it, we can ensure that there's no clashes or unfixable bars. And during this phase, when we're running these animations with the contractor, we can work out, is this sequence the optimum sequence? Is it the safest sequence? And we can also model in things like working areas and working rooms to see how this all comes and fits together during the design phase. Do you want to flick over to the next slide, Dave? If you play this video. So here's one of our final outputs of our models. Just a bit jumpy. So this is, well, it's not even half a building. It's a building with the top cut off. And as you can see, absolutely every single reinforcement bar is modeled here. And we've got a clash tolerance of 3 millimeters, which means that every bar can have a maximum overlap of 3 millimeters. Now that 3 millimeters was chosen, not arbitrary. That is to do with the difference between the actual and nominal bar diameter on a reinforcement bar. So that's where the ribs are. So that allows that bar to sort of nestle in more on site than as it's modeled as just a solid object. So as you can see, we've got 12 million, it's actually up to 60 million at the moment, 60 million pieces of reinforcement bar that we've coordinated on site to 3 millimeters. So that means they can translate that directly onto their construction activities. So it's slow. And here we go inside. My guy bashes his head, but he's not drawn to scale, to be honest. He's just there. It's a pretty picture. And as you can see, even when we get inside, there's about 1 million different embedded items across the entire site that we coordinate against there. Do you want to flick onto the next slide, Dave? So on Hinkley Point C, we've got a large number of densely reinforced civil structures, but we've also got some very unique structures, and one of them is being the volute. This is a natural pump, and it's for the pumping station, so that the coolant water can be pumped to the reactor unit. And that's got a varying radius as it goes around the structure, meaning it's very, very difficult to detail in 3D, never mind 2D. And actually, we had to work in collaboration with the software vendor Declassion because we were really pushing the software to the limit. And Declassion took on board a lot of our learning during the detailing of the structure, particularly the large number of unique curved bars, and have used that to sort of develop their roadmap for future development. So we're really, we're seeing that the Hinkley Point C is helping to really shape how the industry and how the software vendors are wanting to supply to the industry. And also by doing this all in 3D, we can look with the construction teams to deal with issues before they get to site. We worked quite heavily with both the Langelook pre-construction team and their construction teams for the Volue, and we would have day-long sessions where we'd basically make sure that every single bar could be fixed. And this actually resulted in quite a lot of redesign of the structure. So during that phase, a lot of bar layers were switched. A lot of bars, we maybe have to change layers, so from 1 layer to 3 layer to fit in the minimum bends. So by doing this in the design phase, we're able to run all of our calculations, as Dave said, through Contour RC. We're able to refine that. We're able to report the actual utilization ratios, and we're able to give the regulator that confidence. Whereas if we hadn't done this in 3D and we'd done it in 2D to the best of our abilities, when this structure got to site and the contractor came to fix it, if they wanted to make any design changes out on site, that has to go through a very convoluted process where it has to get approved. The design, we're basically changing an approved design, and it needs to get reapproved by the regulator. So actually by doing this out in the design office, we really are securing the program for the contractor and client, because they can't pour concrete unless it's to an approved design. And that is often what causes the most delays in nuclear, in the nuclear industry. Can you flick onto the next slide, Dave? When we've been delivering all of our models in 3D, we've really been looking at what we call digital accelerators. And these are essentially automation tools. And we use these to really drive that left shift. So as we're taking more work that would traditionally be done on site back into the design phase, but still being able to deliver it at cost-effective timescales for the client. So on Hinkley Point, we've developed over 35 and growing tools, and we've seen about a 30% increase in productivity through the deployment of these digital accelerators. And these digital accelerators go across the modeling and design life cycle. So I'll show you some now. So if you just flick to the next screen. So one of our key challenges is the declassion coordination of the plates to coordinate between the MEH and piping design and our civil structure. And as I said, there's over 1 million plates. So if we think about that, even if we try to do it manually, and we said it's 5 to 10 minutes a plate to declash manually, you're talking 5 to 10 million hours that need to be spent just moving a plate by maybe 5 millimeters, 10 millimeters, small movements, but to assure the design. And then if we can't declash it, it then has to go through that loop with the designers. So we looked at this and we just said we can't spend 10 million man hours. We don't have 10 million man hours to spend. We would still be here now on the first model. We need to automate this. So Dave, you flick onto the next slide. And hopefully, can you play that video on the left-hand side? So this is where we developed a tool that will help with the declassion. And the tool itself here is run on the left-hand side. It doesn't look, it's not glamorous. You don't see a load of stuff moving on the model. But what this is doing is very, very powerful. This is looking at every single embedment plate, and it is moving that plate in the background to find a position where that plate could be declashed within our allowable rules. It will then report that position back to us and say, here's all the plates I can declash within the allowable rules, and I've gone and moved those for you. Brilliant. And it said, these are all the other plates that I can't declash within the allowable rules. Do you want me to find a declash coordinate? And then we would run run the second phase, and the tool will report back to us the closest place it can position the tool within its design position. And that means that we can now take this data very quickly to the piping designer and the equipment designer to see if these plate positions that we've extracted and put in Declash are acceptable. So in this example, there was about, I think it was about 100 plates there. And you can see that in about 30 seconds, we have now got all the information we need from those 100 plates. So looks phenomenal. It looks simple, but it's phenomenally complex, and it's probably the most valued tool that we've generated. But we've also looked at tools that we use to generate and speed up production. And if you start the video on the right-hand side, please, Dave. Now here, what we've done is we've developed, especially for the cut and cover tunnels, because they were very standardized, and we tried to get very standardized prefabricated cages. We've developed what we call components that allow us to position the reinforcement based off a set of parametric rules to automatically position these in the model. This has the benefit of these components have all been QA checked, so we know that the lap lengths in these components are right, the rebar sizes are right, all the bending fabrication tolerance is all right. We've ran through the contractor, how these cages are going to be built, and they're happy with it all. So that means that when we're positioning and using these components, not only we're speeding up production, because we're able to, as you can see, place this reinforcement very quickly, but we're also able to speed up the quality assurance because these have all been checked, reviewed, authorized, and accepted by everybody. So it means that when we use these, we can very quickly turn around accurate designs. Dave, if you just flick over to the next slide.
Steve, we're going to have to wrap up fairly soon, I'm afraid.
Yeah, I've only got 3 more slides, so I'll be super quick. This tool here is just for the drawings. If you can you just play this one quickly, Dave? So within Tekla, one of the hardest elements was the creation of drawings and the manual effort it took to create them. So we've developed a plugin that actually takes our model from Tekla into CAD, just AutoCAD, and then it will annotate the drawing automatically. So you can see we're able to bring in all of our rebar call-offs very, very quickly in a very consistent manner with all the information that we need. Just a bit conscious time, Dave. Can you just flick to the next slide? I think I'm nearly done. So whilst we're looking at future developments, one of our key areas we want to focus on is how do we move away from paper construction to model-based construction. We've been toying around with this idea in collaboration with the contractor on Hinkley Point C, as sort of probably as early as 2018, 2019. We have had successful trials, but we've never been able to take it past a trial to full implementation. And that's been down to a few reasons. It's how we present in that data within a model, so that the contractor doesn't have to, point at every bar on an iPad and try and select the right bar and read metadata and work it out. That was a big part of how do we contain that information. And also it's just generally upskill, and how do you mass upskill a large workforce who are used to seeing information in one way to seeing it in a different way. So they're the sort of challenges we faced. We are hopeful we can overcome them, and we'll keep on trying to overcome them as we progress on. And just the last slide here is we're also, for the future, is preparing for non-major projects or non-heavy civils projects. So we are trying within Atkins to push this technology onto all the projects we do, and we're working hard to get that down to be a cost competitive rate. And we've managed to deliver on a number of sort of standard typical building design jobs. So we've done one at Fulham Depot, we've done in 3D, Richmond upon Thames College, we've done in 3D, and also on the Burton wastewater sewage plant we've done in 3D. And we are finding the results are good. We're finding we are able to drive down the time it takes to be competitive with the traditional 2D approach, but with all the added benefits I explained earlier of doing a 3D approach. And this is really where we're targeting for 2022. So sorry I had to sort of race through that towards the end. But thank you very much for listening. It's always great to present at these events and showcase some of the work we're doing.